Welcome to the Current Science and Technology podcast from the Museum of Science in Boston. I'm your host, Julia Sable, and every week we bring you interviews with guest researchers and our museum staff covering science and technology in depth. Saturday, November 28th was Making Stuff Day at the Museum of Science, celebrating advances in materials technology as well as the upcoming series Making Stuff that will air on NOVA next year. The Museum of Science collaborated with the NOVA Science Unit, the Materials Research Society, the Center for High-Grade Manufacturing, and the Harvard Nanoscale Science and Engineering Center. I got the chance to talk with two researchers, both of whom work on materials solutions that will help make electronics smaller, smarter, and greener. First, I'm talking to Dr. Amy Moll, a professor in materials science and engineering at Boise State University. Welcome, Dr. Moll.
Thank you.
Thanks for joining me. So in your public talk at Making Stuff Day, you talked in a general way about how material science shows up in everyday things. And your specific research, it sounds like that applies as well, because I use my laptop computer and my phone every day, and they would not be possible without the field of microelectronics, getting computers smaller and smaller.
Right. So if you look at something like your cell phone, 10 years ago, a cell phone, all it did was make phone calls, and it was pretty darn big. And over time, they've gotten smaller and smaller, and they've gotten more and more functionality. They do more and more things for us. They have more memory, they take pictures, they play music.
Yeah, and one thing that I would love to ask you just to get us started is basically a phone is a tiny computer, right?
Right. So inside any computer or phone or electronic device is a computer chip. And that computer chip is basically made of a whole bunch of transistors, and what they really do is turn on or off, on or off. And they keep getting smaller and smaller and smaller because of material scientists and electrical engineers working on the processing. But in the end, no matter how small you make that brain or that heart of the device, it still has to talk to your thumb. You have to dial things, you have to keyboard things in, you sometimes somehow have to communicate with those little tiny switches. That's where packaging comes in. You've got the chip and all the things, all the transistors on it and all the computing it does, but there's all these layers in between where in the end it really has to talk to your fingers. So that's where the packaging comes in.
And that's what your field is, microelectronics packaging.
Right. So all the materials, it turns out that they have to do all kinds of things. They have to move electricity around. They have to move electrons around. They have to deal with mechanical stability, right? You don't want this thing when you drop it to fall apart. They have to deal with thermal issues because it turns out computer chips heat up, and when they heat up, they stop working as well. And then we have things like screens and displays and all that kind of stuff. So you have all these different performance issues. And you need all different kinds of materials to do that. Metals, you have semiconductors, you have insulating materials, you have plastics, you have all these materials. And you need to get everything into a really, really, really small space.
So of that big array of materials, what particular ones have you worked on most recently?
So one of the projects I've worked on is something called 3D stacking of computer chips. So most of the time what we do, if you open up your computer and you look inside, you see that green board, and you see what you see is the chips laid out like they're on in a suburb, right, next to each other.
Is that the thing called the printed circuit board?
Right. So you have a printed circuit board, and the chips go on that. So all the computer chips and all the other little components go on that. And they're laid out like a suburb, houses next to houses, right?
So I've got a small green thin plastic board. And
It's actually fiberglass.
Oh.
Yeah, the plastic, the green board is fiberglass.
And it has a little network of lines on it, and that's printed metal, right?
That's printed metal, exactly, so that the electrons can move around.
And then you're talking about things that are attached onto the
Right,
metal?
so usually you see those little black plastic things, and they have, like, legs on them.
Yeah.
They look like little caterpillar or little bugs kind of thing. Those inside of those is your computer chip.
Oh, okay.
Could be memory, it could be the central processing unit. It can have different functions. But inside there is the silicon that's making the computer chip.
Okay, and that's what you're dealing with?
Well, okay, so if we have those computer chips and we think of those little black packages as houses, and we think of the metal lines as roads, we've now laid out this printed circuit board like a suburb.
Yeah.
Takes a lot of space, right? There's a lot of space between the houses. If we could now lay this out more like a skyscraper, where you put those chips on top of each other, you're going to save a lot of space.
Yeah, that's a great analogy. That's just like what they do in the most populated parts of Boston.
Right. So now we have to have ways for the chip to communicate from the top floor to the floor below, to the floor below, to the floor below. And we can go outside with the wires, but we start to run out of space. So one of the things I've worked on is the ability to do what we call through wafer interconnects. We drill a hole, basically in the silicon chip. We fill it up with metal, so it's like a wire. And now we can communicate from the top to the bottom of that computer chip instead of basically crawling on the outside. We've basically built an elevator shaft inside the skyscraper. And it sounds really simple, but it turns out it's not that easy to do because
the skyscraper is really, really tiny.
That's right. So you can kind of think of it, the scales sort of build up. Each transistor is so small now, each on-off switch, that we can't see it. But you put millions and sometimes billions of them onto a single chip. But that chip now is big enough that we can actually see it. And now we're stacking those up into 2, 3, maybe 4 layers now.
And each layer is what you're calling a wafer.
Yeah, or a chip off a wafer.
So it sounds like you're involved in designing the wafer so that there will be these spots that you can drill.
So you basically have to introduce some new processes into the process of making a chip. You have to be able to drill these holes through it, which are really, you want to be as small as possible because this real estate is very valuable. We can't mess up the devices that are already there. And now that we've drilled a hole that's deep but really narrow, we have to try to fill it with metal. That's not easy either.
Oh, does it require specialized kinds of metals?
Right. Well, it actually requires specialized processes. Typically, we're just using copper, but being able to fill this very narrow hole is actually quite complicated.
So what have you done regarding solving that challenge?
We've been able to work through the processes to develop the ability to dig the holes and to fill using electroplating with copper. So we've been able to demonstrate this ability to basically build a wire through the chip. And now we're starting to use that to stack different things together and make sure that the devices still work.
Are there any examples of devices in actual use that have this 3D stacking in them?
Yeah, actually your cell phone typically will have a stack of a couple memory chips on top of each other. Most of those, the practice in industry right now is to pull wires on the outside, kind of like running an elevator on the outside of the building. The technology to drill the holes, although it's been developed, is not yet in production.
How long do you think it will be until it does get used in a cell phone, for example?
I think you might see it in the next couple of years. It's developed enough. It really comes down to whether it can be inexpensive enough to actually make it into your cell phone, because people don't necessarily want to pay more money for their cell phone.
That's for sure. But they would love to have a smaller, more compact cell phone, or maybe a phone of the same size that you can pack in even more memory.
Even more memory. So I think you might begin to see it in production within the next 2 or 3 years. Of course, you won't actually see it unless you rip your cell phone apart.
What are some other applications of this 3D stacking technology?
So probably the first one you'll see is something like memory chips in a cell phone. But this has some really other interesting applications. A lot of different researchers are working on sensors that can detect things maybe in your blood or in other liquids that might not be good for the chip, the computer chip underneath. So now you can build a package where you have the sensor on an outside device. You use these connections through wafer interconnects or through silicon vias, and you can protect the computer chip underneath that's going to do the processing of the signal. So imagine I can put a drop of blood on top of a sensor and have all the computing right next to it, but protected from that blood.
It's definitely true that our newer devices have a lot of different talents in one unit.
I think one of the very new and developing fields really is medical. Can you do different tests at home where normally what used to happen is you'd go give a blood sample or a urine sample. They take that, they send it to a lab somewhere else. You wait a week. They call your doctor back. He calls you back. It takes a long time. We're starting to see some things where it's now in the doctor's office. But imagine you can start to do things where you can do more testing at home.
So it sounds like in the next few years, this could start to be used, but a consumer like me won't even notice, right?
No, probably as a consumer, you'll never notice what's going on inside your computer or inside your new device or inside your cell phone. You'll just notice that you have a lot more memory and a lot less space.
That's great. I've noticed throughout this Making Stuff Day that there are all these amazing materials that are invented every year for stuff that I use every day that I never even thought about. So this is another example of that. So thank you very much, Dr. Moll, for joining me and explaining your work today.
Thank you for having me.